Uh, Today's pickup was arranged by Richard Traverso, our undergraduate coordinator, and so I'll ask him to come up here and introduce. All right. Yeah. Just.
All right, thank you. So James Dellinger of the National Institute of Aviation Research's Environmental Test Lab is going to be our speaker, and he had reached out to physics about some opportunities for undergraduates, and so he's going to be talking a little bit about that today. Probably a little bit shorter talk than our nominal time of 50 minutes, probably about 40 some minutes, and then he'll be meeting with students afterwards. A couple remarks about Jim. He has 45 years experience in engineering and engineering management. He worked at Hawker Beechcraft, which it's now Textron, and he worked with qualifying and developing and certifying some of their core systems for some of their flagship products, the King Air and the Hawker, some of the Hawker systems. He's worked for the National Testing Systems Laboratory. He's worked for Ingenium Laboratories, and he's been at NIAR for 6 years, where he is the director of the ETL. His specialty is mechanical systems, landing gears, hydraulics, and all the certification qualifications for that. And his title is Safety Comes First, or Safety is Paramount. And so I thought this was a really great talk to showcase the kind of work that NIAR does to physics, in hopes that we can have some of these other speakers from NIAR and the Innovation Campus showcase their great work to faculty and also students about the opportunities that are available. So without further ado, I'll hand it over to Jim and help me welcome our speaker.
Thank you. Can you hear me okay? Okay. Bring that up a little closer. Yeah, and also I want to introduce my colleague that's with me here today, Nick Conquest. He's the operations manager. So when we meet later on today, you know, pick both of our brains. Will be good. So maybe I'll just set that there. So really, safety through testing is, safety is paramount. How many people in here have never flown? Go ahead, raise your hand. It's okay. Okay, one person? Okay, so every time you go get on an airplane, if it's a small little general aviation aircraft, a business jet, or a big iron, we call them. So, the Boeings, the Airbuses, Embraer, all those folks. What we do down at the laboratory, we do for all those types of aircraft. Okay, so it's very important that what we're doing down there and what we test and all those kind of things that we do are super, super important to the aviation community. And that's why I think it's really cool that you guys have an opportunity to hear what we do and then potentially come to work with us. Oops. Doesn't move as fast as I think. Okay. So just want to put that up there. I mean, you guys all know this, but if you take these principles that you're learning in physics and then you listen to what we're doing down in the lab and the types of tests we're running, you'll draw straight correlations to these that you're learning in the classroom and all the textbooks, things that you're learning. And that's why it's important, okay, to understand that. So our mission is to improve the safety of the aviation industry, because safety is paramount. We partner with the industry people, okay? So from Boeing all the way down to a small organization that might be making sensors, okay? To work with them on qualification, testing, certification. We'll get into that a little bit more. Is it, what's going on? Is it on a timer? Oh, how do I get out of that? Okay. From our engineering staff and staffs, we work with engineers as far as with the industry, certification, qualification, and testing. It kind of goes backwards. So we've got to perform these tests. These tests we're doing are qualification tests. once you qualify a system or qualifying a system, then it goes into the vehicle that you're going to certification. If it's going to be a type certificate, which means a brand new aircraft, or if it's a supplemental type certificate, like I've already got an airframe that's already certified. I'm going to put brand new engines on it now. Okay. That'll be a supplemental type certificate. But we still have to start with that testing, qualify that into the certification plan, and then show and find compliance, which we'll talk about. Important for you guys here is all that is that you're going to work with some people who've been around a long time, who've done these types of things along with the testing. But for you, it's the applied learning. Now you have the opportunity to come down and work in a laboratory, and there's other labs on it, not just mine, at NIAR, that you can work in that are going to have physics principles that are going to get applied. And it's important for you to see that outside of the classroom. And I'll say for our laboratory, we have many specifications. We're going to talk a lot about DO-160 that comes out of RTCA, which is mostly for commercial aircraft, but we do a lot of other specifications. But one thing about what we do, they don't teach in school, okay? Because the type of tests we do, the equipment that we use, the setups of the test, you just can't learn anything. So if you were to go to these laboratories and work in them, when you walk out and go to work for someone else that's in that field, you're way, way ahead of the curve. Meaning, I was in my mid-30s before I started seeing some of the stuff that you would see at 18, 19, 20, 22, 21 years old, okay? So it's really cool and important. Okay, so I talked about specifications. We'll get further down the road on this. So DO-160 is what we're going to talk about a lot. Then we have 307, RTCA, portable electronic devices. That's where people certified the airplane today. So you can take your laptop on the airplane. You can take your phone on the airplane. You can do this, you can do that, because we're going to look at how that RF and other energies come in through the back door on the cable bundles, or it comes in the front door on the antennas, okay? And then we got unmanned vehicles, 227, which is being a really big deal for us right now on non-rechargeable lithium batteries. So we'll talk about that as well. And 311, which is rechargeable lithium batteries. Okay. And then we have subject matter experts in all those. So like I said on 227, but we have other folks that are on the Lightning Committee. We have people on the High Intensity Radiated Fields Committee, which are having a meeting right now at SAE, and we work on all the documents. Okay, so we're leading edge of what's new, how we're going to do the new test, or how we're going to change the test, and all those things. And then we work a lot on the fire procedures and regulations with the FAA and SAE. And then we do a lot of work with the FAA, meaning they come to us and say, hey, can you do this type of test with gases? You know, we have had a few airplanes go down because, okay, we had an ignition source, blew the wing tank up and crashed the airplane, you know. So that's some of the things that we're doing. Okay, so then with our staff, we have designated engineering representatives, DERs. So those are the folks that have the ticket. So they audit, watch all the tests. They work with the project-specific certification plans. And then they're the test witnesses, and they do design reviews for, if it's from all the regulations, because you have to show in all the regulations how you're going to say this is a compliant system to go on an aircraft, and then ground test, flight test, and finally get it certified. These gentlemen work on those, and they provide compliance statements, but they're the eyes and the ears of the FAA. And so we have those folks on staff. And then we have multiple engineers, disciplines from electrical, mechanical. We don't have anybody from the physics department right now, but we have had in the past. So that's one of our reasons we want to do that. And we do, mechanical, electrical, direct effects of lightning testing, And then again, design reviews from a different perspective. So the DER does it from one level, it's about compliance. And we're looking at it from, okay, how do you meet this certification over here with DO 160 or MIL Standard 810 or 461, so on and so forth, because we're the experts in that field. We do, we build test plans, procedures. So a plan is what we're going to do, procedures, how we're going to do it, okay? With all the goodies that go with it. And then we conduct test readiness reviews, and then we perform the test setups, and then we may troubleshoot with the customer if they're having issues in specific tests. We try different things to help them out. And then this continues. We work everything that we do, we have to have collect the data, right? So if we're doing a vibration test, we got to collect all that data so we can build the charts that says, okay, I was within this tolerances, I was running these frequencies, I was running this G level, so on and so forth, or I'm over here doing radiated susceptibilities and I'm going through 100 megahertz to 18 gigahertz in all these steps with this amount of volts per meters. We got to collect that. So we're using NI-DAC quite a bit now. We've used Agilent in the past as well, but familiarization with data acquisition. Is it? Okay, it's not doing that to me. Then we do the report, and that's the most important thing for the customer at the end of the day, right? I get all this testing done, but I got to have that report, but I got all passed all my tests, okay? We do hydraulics, pneumatics, and hydrostatic testing. That's a little outside of that window. And then we do designs for vibration, fixtures that hold those. So you could be involved in that type of stuff as well. Then we do conformity, because you have to know the pedigree of what you are testing. So the test article has to be conformed. The test setup has to be conformed. And then it has to be FAA conformed. So we do all those things to make sure that what we are testing has its correct pedigree, and then we can move on with the test. So I picked this to kind of give you a pictorial of, so this is flight controls. Okay, so from the controller up front to the flight control computer, the actuators that goes to the elevator, the aileron, the rudder, those could be all LRUs that we test. There are sensors in these systems, so it could be that small of a component that we test, or it could be like right now, we have a whole avionics flight control system in our reverb chamber that we're testing for a customer. So it can be a little small piece, or it can be big LRUs, small LRUs, or the whole system that we test. So that gives you kind of a pictorial of the systems level that we're working at. And as we go through that, I'll give you, so then we do like avionics systems. So it could be displays, or it could be a whole piece of the avionics with navigation, communications, flight management systems, autopilot systems, electrical systems like power generation. So it could be anything from small generators, right, all the way up to some massive generators that go on like 787s that you could be testing. Storage management systems, just to give you an idea. Engine controls, and a lot of these things that we're talking about that makes the world so safe is that, so there's DAL-A systems. So a DAL-A system is a system that you can't lose. It means I can bring the airplane home, safe flight and landing. So we protect those with backup systems to make sure that we're all safe. You get down to a DAL-E, it's kind of like, oh, well, okay, so the stereo went out, not a big deal, right? And we're going to still come home. But most of these things that we are testing are mostly in the DAL-A, DAL-B arrangement, DAL-C. Okay, and then just here's some other components, systems, hydraulics, landing gears, wheels, tires, and brakes, oxygen. So everything that goes on the airplane. So we're going to talk about RTCA, not a great deal, but it's been around for a really long time. And so that's why the specifications are very well put together. where you can pick categories. You got to be able to understand where your installation is going on in the aircraft. And then you can determine, okay, this is the type of testing. So there's two things that I'm telling you is that I'm talking mostly about the testing, but if you think about what I'm telling you, it's also if you were to go work for someone and you were a design engineer, okay, you have to know all these things about pressures, forces, temperatures, blah, 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 to make sure that those items you're covering and knowing what test to apply. So that's important as well. So what we want to do is make sure that our systems are being tested at the appropriate levels, okay? And RTCA DO-160 has a lot of great information in that, and I'll break that down a little bit as we go through here. Oops, back one. Okay, so source, path, victim. Okay, again, this goes back to what I was just talking about. If you're an engineer, okay, I'm working on that, but if you're down here in the lab, you're gonna, okay, we're creating the source somewhere, right? And then it's got a path that it's got to take. And then it's got a victim. And typically, sometimes the piece that we're testing is actually the source. Most of the time it's the victim, but the path is important too, because I can have something over here that's creating the source, but as it goes through the path, it changes before it gets to the victim, right? So if I took vibration as an existing part and said, here's two engines running, right? That level of vibration and frequencies at the engine is going to be different when it gets to a certain level in the aircraft, right? So we got to understand that. But DO-160s and other things help us do that. And again, here's some sources. If it's light, temperature, RF transmissions, high-speed data, traces, electrical motors. I'm not sure why we have arc welder in there because we're not flying with one. You know, video displays, pressures, temperature, and then the path is like, okay, I got stuff going through cables or up through an antenna, common grounds, power lines. Parasitic capacity is a big thing when we get into lightning and those kind of things. And then inductance. And the materials and structures, and then the victims are the integrated circuit cards, the RF receivers, telephones, blah, blah, blah. You can, it says I have to restart. It says it's restarting. To it to be hurt or not function. Lightning direct effects. So I know Nick talked about this a little bit. It's one of our fun tests in the lab. So again, he talked about it's a probability of one airplane's going to get hit by lightning. So we got to design to make sure that we can take the strike, and then we'll talk about indirect effects in a minute. But what we do is on the left-hand side down there where the flame's at, that's where we can produce 200,000 amps, okay? That's the A level strike on a lightning strike because you got an A, a B, a C, and a D component. That's the highest level, and then it comes off, and it all happens in 18 nanoseconds. That's what that strike is. And so that's where we do the high current. The right-hand side over there is where we do the voltage. We can produce around 400,000 volts. What we're looking for there is how it attaches. So if I have a flat panel like this, I'm just going to say, I'm going to go over here and do it in the current side because I know I'm just going to hit it on the panel. If I have like a radome, the front end of the aircraft, I'm going to want to figure out how does it attach to that surface. That's where the voltage comes in. So voltage is like little tick, as you can see down there, and it's very quiet. The other side, the 2,000 amps, 200,000 amps, is like a shotgun going off, okay? So they're totally different environments, but you can't do them the same, or we'd shut down Wichita if we tried to produce a generator that could do that. So that's what we're doing in the direct effects, you know, and then a lot of that stuff is, we have antennas on the outside of the aircraft, we have fuel caps that are on there, we have vent systems on the fuel tanks, we don't want those things to also ignite. So those are some of the other things that we're looking at as well. And then how do you dissipate? So design goes around, how can you dissipate that? Aluminum aircrafts are really good for that, okay? Composites, not so much, right? So that's why we have copper fibers in there and all kinds of other primers and paints that are good for lightning strike protection. But again, we test all those things. And then Nick was also talking about, again, back there in direct effects, we have a box you can mount the panel on. We put that ignition source slash, which is the current level, but we have the gas in the box and see if we hit a fastener, does it ignite it? We hit just a panel, does it ignite it? And that's a lot of stuff for 954, 981 rules within the FAA. So we do a lot of work, as we talked about earlier, with the FAA. Okay, so then lightning-induced transient susceptibility. So that's what we call indirect effects. So we just got hit by the lightning, right, on the aircraft, and we're flying along. But now it went through the structure. It got on the cable bundles, okay? Now it's going on a cable bundle, and it's going to my flight management system, all right, which is a really important piece of, or my flight control system, or autopilot. Well, now we have two ways of checking that. We can do a direct pin injection on the power leads and certain pins to make sure that it will survive. It's usually a big killer in the test to see if they can survive that. That's where people fail the most. Or then we clamp it and we run current down the cable bundle and it goes in naturally like it would through the airplane, right? So we look at it in two different directions. But you're going to get energy through the fuselage, through the wings, through the vertical, down into these systems and on their cable bundles into the pins. So it's a huge test. Electrostatic discharge. So, so everybody's played the game at their house where they scuff their feet and, fun with your buddy. Well, we do that because it's real too for us. So there's going to be some electrostatic discharge within just natural physics things that happen, right? And so we have the machine right there that actually can produce the 15,000 volts. And what we do is we we hit that unit 10 times around it to make sure that it can survive that ESD discharge. Then we do full vehicle testing. So basically we go out to a full vehicle and lightning transient. So we do lightning tests. So if you can tell on the top, there's this structure that's around the fuselage and the aircraft. That's what we call a return array. And so we're going to put a small amount of current into the aircraft and it's going to come back through that array. And then we can measure what that coming back from the aircraft looks like, and then we can extrapolate up to the levels for that particular airframe, because not all airframes are built the same. And then we also do high intensity radiated fields. So the one below that is where we're doing the HERF testing, and that is a low level swept fields test. So we're radiating energy to the aircraft, and we're measuring the levels of what that looks like on a return signal. So then we can determine what do those fields look like. And then on low level swept currents, we go and inject the current level right on the fuselage. So it's not, we don't have a setup show for that, where then we can measure on the cable bundles what that current looks like and extrapolate it up. So then does it match what levels in DO-160 or something, or does it have a special condition that we need to test to? It is higher or lower. So those, again, you can see all the bells and the whistles that we're putting on these LRUs, the system, the safety of the system, and testing it out so us, the flying public, comes home safe every day. And then we got the portable electronics. I mentioned that earlier. So again, that's how we are able to bring all of our electronics on. And one of the things I always like to tell people, it's not that they don't want you to play on your electronics. They just want your attention from 0 feet to 10,000 feet. And the reason why is because if we have an issue from 0 to 10,000 feet, they need your attention to respond. Okay, I get to 35,000 feet and I have an issue. I have a lot longer response time in the aircraft to get people in this situation and that situation, but really from 0 to 10,000 feet. And that's why also we want them turned off 10,000 feet to 0 when we land. Again, it's an attention thing. Do we all know what's going on? But again, that's how we get portable electronics devices in, by doing those front door, back door tests to make sure that nothing's being upset from the cable bundle side of it or the antenna that's coming up through on the coaxial cable. And then we do source victim for EMI testing. So turning things on and off that says, okay, if I turn this one off and turn this one on, or I turn them on together, is it the same thing about that susceptibility where we're talking about adjacent boxes and stuff? This is another way of checking it, but now we're at the aircraft level, turning them on and off and making sure that they don't have any disruptions on that test. And then P-static or precipitation static, just flying through the air, right? So sometimes we go out and flood aircraft with, 50K up to 120K volts with a wand and look at different parameters on the vehicle to see if they're having issues. Sometimes it's like windshields have a lot of static dissipation issues sometimes, but static wicks and all those things that are on the back trailing edge of the wings and the surfaces on the horizontal and the elevator typically take care of that, but we can also test those to make sure that they're operating correctly as well. Some of the just other tests that we're doing right now, 227, which is the non-rechargeable lithium batteries, has gotten really big. And so what we're doing is we're doing all the cell level testing. So we'll take cells and take them through vibration, temperature, humidity, altitude, decompression, and all those types of things. And then we also do short circuit, overcharging, those types of tests, capacitance test. And then the fun test is thermal runaway. So we have a chamber down there now where we put batteries in an LRU that is going to be in the airplane and it's a backup battery. And we actually put it into thermal runaway. So we force it there to see what it does. And then we also pump the gases out, see what kind of bad stuff it's putting off and what the levels are. So if it's cyanide or CO2 or whatnot, we can measure that as well. We can see what the pressure spike looks like. And similar to, we can do that with rechargeable batteries. We just haven't got to the point of doing really big battery packs yet that are all going to be in the eVTOL world, right? Or electrical vehicles if it's standard flight mode with big batteries. And then we do radome transmissivity testing, which is basically that is looking at the window that the radar is going to look through. So we have an antenna down here. We're transmitting through the backside of the radome, right? And then we're seeing what the return looks like. So it's at 0 degrees. Then we adjust it to 45, 80, and there's more in between there, up and down. And then we switch it around because we can't change the antenna because it's lasered in with the receiver at the other end. And so we change it and then we do the same with that. But we're looking through the window just to make sure that a lot of repairs, are they repaired correctly as well. And so these are all the other standards, and I mentioned some of them as we went through, but we talked a lot about DO-160. But here's a lot of the other standards. I didn't put any ASTM specs up there, but we do some of those as well. Couldn't list them all, but we do a lot of testing down there, and I think it's right in your guys' wheelhouse if you're wanting that applied learning. So here's my contact information. Here's Nick's contact and John Rehard, who's another manager. If you're interested, we'd love to hear from you. If you're interested, we would like a resume because we want to interview you. One of the things I always tell folks is that young students, you don't have to have any of this experience, okay? If you come with experience and you like to play with computers and tear them apart and so on and so forth, or you like to work on cars and so on and so, whatever that is, more the better. But again, what I told you in the beginning, what we do is something that nobody's going to train you for other than working in a lab like this. And again, if it's like up at Aztec as well, it just, you can learn a lot of principles, but putting it to use and learning it is two different things. And so with that, I want to say that I appreciate your folks allowing us to be here, allowing us to discuss this with her, present this to you, and all your time. We feel very good about it. I was excited to get to do this. I know as Nick is probably will do the next one if we have another one. Yeah, thank you so much. Now, is this a time where we can take questions? Thank you.
Yeah, it's already after 3, so if anybody has to run, please feel free to leave, but we can take questions, yes. Anybody back there first, maybe? Yeah, no one.
Go ahead.
So I have a question. Like, of course, there are new sensors and new technology moving every other months or daily. So, do you care for whether the instrument that we are using or the software automation we are using it over-engineered, and how do you work?
Repeat the question. I know it's about software. How do we overcome the engineering? Over-engineering. Okay. Well, one of the good things about it, the industry today, is that we have the FAA guidelines, okay, which specify certain things that you must do, okay? And then we also have these testing regimes, okay? But so we have a pretty good set of requirements that guide us to not over-engineering, okay, things. And if you talk about software, you know, there's a whole section about DOS 178, which is your software itself, and then you have 254, which is all about the firmware that goes inside boxes, which has their guidance and the lower and uppercase test regimes you have to go through there. So we really have a good set of requirements that we should not over. Now, what we do is, like I said, those DAL-A systems, we overprotect, okay? Because we have to bring the airplane home, okay? We have an issue, we got to bring the airplane home. Great question.
Opportunities for developing sensors in NIAR, or is it only focused on testing the sensors right now? Are there any opportunities for working in sensor developments for aviation?
Sensors? And when you say a sensor, what do you mean?
Sensors for different tests that you're using. So I was just wondering if there are any researches going on the sensors, or are we testing the ones that are already?
Well, we're typically testing the sensors. Yeah. Doesn't mean there can't be research for new products, right? So that'd be, but I think to go back to, what was your first question? Oh, so if you do a brand new airplane, today you're probably looking at 7 years for a complete cycle, meaning because we have all the design that has to take place, okay? So you got preliminary design, you got critical design review, and then you start building chips or building the aircraft after critical design. So you build an airframe, now you've got your suppliers on board that says, okay, you're going to take this system and you know what the requirements are now. And so then they have to go start building hardware, and they go into this regime of testing as they're building other hardware. We put that on the aircraft and we start doing, because we're going to fly this thing under experimental ticket until it gets type certificate. But again, then you've got ground testing before we ever go fly it, we're going to take all these things, and we're looking for safety of flight information. So that's usually quick tests that we can do. This gives us some assurance that what we are going to go do is we're not going to have an issue. It's not all complete, so there's safety of flight. Then we do ground testing. Then we start doing flight testing, as all this testing I just talked about is running in parallel type of stuff. So an STC might be 3 or 4 years. Yes, sir. How do I get back there?
Curious about the component that was being struck by the high current. Looks a little bit of a dull red, and I was wondering if that's
I'll find that.
component happened to paint it dull
Anyway.
red. Actually good.
Oh, I don't see this. There's the cursor. Where's that?
Just click and hit up, I think should work. Just hit the up arrow. Few more, something on.
Oh, I didn't see it. It's coming up behind me. Okay.
Yeah, the red plate.
Oh, that's a test plate that it's setting on. Yeah, yeah. Fiberglass, yeah. Yeah, that's a copper strip.
You managed to catch an airplane picture that was being struck by lightning.
Really fast camera, but I'm not the photographer. Yeah.
Yeah.
Oh, yeah. Yes, sir.
So first of all, I really wanted to say thank you for coming in and speaking to our physics group about these opportunities. I do think there are a lot of synergies between what you guys are doing and what training our physics students can do. So just for the students, a lot of what you're talking about is, system design and testing systems, and putting integrated systems together and understanding how they're going to work, which is what we do in experimental physics too. We often build complicated devices and have to understand how each component will work in its environment and if it's safe for the people to use it, and what kind of false signals are we going to get through it. And learning how to think about, in this kind of engineering mindset, how to break down complicated systems and their components and test them is a really important skill for experimental physicists to develop. So just wanted to throw that out for the undergraduate physicists here. Like, aside from you applying some of what you've learned in introductory physics and what you might learn there, the skills you might learn working in here are very applicable to come back into physics. Sounds like a really exciting.
Great comments. Yeah. Yep. For sure.
I have one question. How do the tests evolve over time? It's a lot of the environment doesn't really change that much, but with climate change, maybe storms get more intense or more frequent. Are tests changing to take those things into account, or are the standards pretty much the same as they were 20, 50 years ago?
So they do change. Okay. And it's usually more of how we run the test. The levels that we test to are pretty well set, unless we find something, because if we're just talking about, we'll just take climate change at its face value. Okay. What we're testing to is minus 70 degrees F plus 165 degrees F. It's sitting in here. We're at all the upper and lower conditions of that as it goes through. So that doesn't really make a difference to us, right? If I'm sitting on a tarmac over in Dubai, 165 degrees on the tarmac there, we have a few degrees. Now, storms, it's still the same thing. We're going to blast these things with all kinds of blowing rain, and those types of things that are going to make sure that they're still safe. We're going to, if it's going to be in an area where it's going to get drenched, it's going to get drenched, right, for those standards. So, but we do that. I mean, our TCA DL160 is revision H is coming out. So you can see over the years, it's changed, right? We just went through on 227, which is the non-rechargeable lithium batteries. It's already to be, but it's only been out for 8 years, I think. So yeah, we work on the standards, and that's part of our expertise. Nick sits on some standards. I sit on some standards. We got some guys at the Lightning Committee, HERF Committee right now this week. But again, unless we find something that is, the world changed hugely, then we would have to adjust to that. But it's pretty well set on that. Does that answer your question?
Yeah.
Okay,
that's
okay.
All right. One more.
Can I ask more out of
Yeah.
question?
Sure.
Right, so,
Yeah.
Have us around radiation parts of devices like neutron radiation or?
We do not. Yeah. We don't have any of that. No. I mean, there's some, I think, Pax River. Yeah. But we don't have anything in our lab. Yeah. Yeah. No problem.
It is a threat to aircraft.
Yeah.
Especially up in the higher atmosphere.
Right.
Obviously more significant for aircraft. Ground
Yeah.
based,
Yeah. There's nuclear hardening is an issue. Yeah. Mhm.
All right. Well, thanks again
Yeah.
for the presentation and join us again a week from today. Have a good afternoon.
Okay. Thank you. Thank you.